Okay, I'm going to... Welcome back, everybody. I hope you can hear me well, everywhere where you are. So I just wanted to repeat some of the things which we discussed on Monday. And today, I wanted to link things more up to the exercises, which we will have on Friday. And again, feel free to hang around if you have the possibility after the lecture. I think this place is free, so we can actually use this place after the lecture. So if you wish to hang around and discuss exercises, feel free to do that. But I'm going to link the lecture today more towards the homework, which we have, because many of the things which we will have to deal with in the homework, they deal with the topic which we have been discussing in the lectures. And then I wanted to give some hints and advice about how to set up things for the numerical exercise. And for the numerical exercise, you can actually use what you did in homework number 3. And if you didn't succeed in finishing homework number 3, you can always look into the solution, which is at the GitHub address. So you can always download that one and use that one in the studies of this falling object. And the thing which I wanted just to quickly remind you a little bit about is this figure which Julie made last year, which I think contains a lot of the information about forces and so on. So this specific figure here, let me just reduce the fonts a little bit so that we can see it properly. So this figure contains many of the connections between the quantities which we are studying. So the first exercise in the homework this week is essentially you looking up what we went through in class last week. And you will also see many of these definitions in the textbook by Taylor. And this deals with angular momentum conservation, conservation of linear momentum. So one of the things which we didn't prove on Monday was the conservation of energy when we have a conservative force. So that's one of the things which we are going to fill in today. And then we are going to jump a little bit back and forth between some theory and then things which are needed for the homework. And hopefully then on Friday, we can use most of the day or most of the lecture which we have for just solving the next homework, if that is okay with everybody. So we get some more time to practice and look at the exercises. So the thing which I wanted to quickly remind you about are some of these properties of conservative forces. And the exercises which we will do in class today, some of them, and I think that for some of you, they may perhaps be a little bit too easy, but I just wanted to look at these two particular exercises. The first one may be almost an offense to you guys, because it's pretty straightforward, whereas the second one needs some more attention, because it has X, Y, and Z in the denominator and in the numerator. And this is the kind of expressions which we will deal with when we look at the gravitational force. So what you see there is nothing but another way of writing the gravitational force without us specifying the constant gamma. And this kind of force is something which you would also get if you were to use the static Coulomb interaction. So if you're looking at two charges which repel each other, then the force would look like this one as well. Except that the only thing you would need to do then is to change the constant gamma. So these kind of expressions for forces are some of the kind of generic forms which you will encounter later in different physics courses. And we often see that these forces actually are connected with some fundamental laws in physics, like the gravitational force. Okay, let's take a look at energy conservation and try to wrap up the stuff which we did on Monday and quickly remind ourselves of some of these technicalities before we then switch back and forth between exercises and exercise solutions. Any questions so far? Things which are unclear? Let me just switch back to the whiteboard so we can do some of these derivations. And the thing which we did last time was to set up some of the basic definitions for conservative forces. So let's quickly remind ourselves about that. So if we look at some of the basic properties which we use to label a conservative force, conservative forces. So one of the necessary properties is that the force depends only on the radial degrees of spatial degrees of freedom. So there is no dependence on velocity. There is no explicit dependence on time. However, R, which you see there as the argument to the force, can depend on time. And we know that because when we solve Newton's equations, obviously we are looking at the dynamics of the system. And that means that the trajectory an object takes will depend on time. So when we're going to prove energy conservation with these forces, then we need to be a little bit careful when we take derivatives because R depends on time. But the force itself does not explicitly depend on time. Okay, so let's just move on and list some of the other properties. And one of these is that the curl of the force, and we have several exercises where we are going to deal with that, is equal to 0. And this leads to the path between two positions being, or rather the work which is done between two positions, 1 and 2. So we would have an R1 here and an R2. And this is integrated over R, multiplied with the force. This is independent of the path we take. Another very important property which we saw last Monday, is that if we have these properties, then we could define the force as the gradient, negative gradient of the potential. And this is also something which we're going to play around with. And you will see in one of the exercises this week, exercise 5, you can actually, when you have the potential, you can plot the potential. And this is often called a potential surface. And from that one, you can say something about the motion of the object under the influence of this potential. Okay, so let's just continue and write out. So this means that we would have minus, and then we would have a d dx of v of r multiplied with the unit vector in the x direction plus the derivative with respect to y. So this is just a definition of the gradient, plus the derivative with respect to the final axis z if we are in 3 dimensions. And this is multiplied by the unit vector. So this will be the expression for the force if somebody gives us the potential. Alternatively, if you have the force, if you can measure the force and make a model for it, you could actually extract either a fundamental force or you could get an effective potential based on a measurement of the forces at play. Now, one of the things which we didn't prove is that if we have these properties of the forces, then the energy, dE dt, the derivative of energy, is equal to 0 with respect to time. And that means that energy is also a constant of the motion. Energy is conserved or a constant of the motion, which is another way of saying the same thing. So let's prove that. In case we have a potential which now depends only on the spatial degrees of freedom. So we are assuming now that V is a potential which depends now only on the spatial degrees of freedom. We know that the energy is given by kinetic energy. So let's assume that we have just one object with the mass m, and this is given by V squared plus the potential energy. So we can rewrite this one as 1/2 of m times of v times v plus v of r. And then what we need to do now is to take the derivatives of this quantity. And what we're going to do then is that we need a derivative of the kinetic energy and of the potential energy. So if we now rewrite things here, we can rewrite this in terms of 1/2 times m. And then we have obviously Vx squared when we write it out, Vy squared plus Vz squared plus this potential V of r. Now, what we do next is we take the derivative of the energy, dE dt, and then we take the derivative of the x component, the y component, and the z component. So this is not the most exciting thing we're going to do now. So we would get a factor of 2 times v of x of dvx dt. We don't know the time dependence of v. We only know that the velocity is time dependent. So this is again because velocity is given in terms of the integral of acceleration from a given initial time to a final time. So we are explicitly assuming now that the velocity does not need to be a constant. So the dynamics of the system, when we have the acceleration, as we've seen before, is governed by the velocity as a function of time and position as a function of time. So that's why I'm putting up dvx dt here, because we have an explicit time dependence in v, and we don't know what that looks like until we have specified it. And then we would then have plus 2 of vy dvy dt plus 2 times vz, and then you see that the factor of 2 disappears. But when it comes to the potential now, we have to be a little bit careful. So I mentioned that the potential depends only on r, but the position itself has a time dependence. So this is actually an implicit time dependence, which we don't know, but there is a time dependence. So that means that when we take the derivative of the potential, we have to be a little bit careful here. So when we now look at the potential, what we will get is a dv dx, the partial derivative, and then we have a dx divided by dt plus a dv dy multiplied with a dy dt plus a dv dz with dc dt here. So that's the derivative where we now take into account that this also contains the time dependence for the position in the same way as we had a time dependence for the velocity. Now, if we now go back to these expressions, we know that the derivative with respect to time or the velocity is acceleration. So this quantity you see here is nothing but the acceleration in the x direction. This quantity here is the acceleration in the y direction, and this is the acceleration in the z direction. So that means that we can, if we multiply with m, we can replace everything with forces. So if we look at the first term here, we get rid of the factor of 1/2 because we have a factor of 2. We have m times acceleration, so that's the force. So what I get now is f of x times v of x plus f of y times v of y plus f of z times v of z. So I'm just rewriting the kinetic energy in terms of forces. And then if I now look at the potential which we have here, what we remember now, since we have this definition which you see here, this specific definition, then we know that the dxv is the same as the force in the x direction, dyv is the same as the force in the x direction, in the y direction, and same for the z direction, and with a minus sign. So note the minus sign here. So every component here is a force in a given direction. So that means that I can rewrite the potential, which we have here, these terms, as the forces, and then I have dx dt, and we know that this is the same as the velocity in the x direction. This is the velocity in the y direction, and the velocity in the z direction. So each of these terms here, so this becomes minus f of x This is V of x, and this is minus f of y, if we follow the definition, times V of y, and minus f of z multiplied with V of c here. So what I get now is minus f of x of V of x, minus f of y, V of y, minus f of z of V of z. And this is equal to 0. So that means that energy is conserved if the potential has this specific property. And we can obviously rewrite this in the vector form. So in vector form, what we would have then is the following. So we would have the kinetic energy of d dt, and then we have m times v divided by 2 here, plus v of r. And then when we take the derivatives, this is just simply going to be equal to the following. So we will have m times v derivative with respect to time. So it's a dot over v. And then I get plus the derivative of the potential multiplied with the time derivative of position. And that's nothing but v times f minus f times v. And this is equal to 0. Any questions so far? So these are what we have proven now, assuming that we have a conservative force, which depends only on the spatial degrees of freedom. We have shown energy conservation. That does not need to imply that we get conservation of angular momentum or that we get conservation of linear momentum. And I don't know if everybody has been able to solve exercise 3. So how many of you have solved exercise 3? So in exercise 3, you have a potential which depends on an exponential, which has as argument x squared and c squared. That potential leads to a conservative force, so energy would be conserved. But what you're going to notice when you run the calculations is that linear momentum and angular momentum are not conserved. So energy conservation by itself does not necessarily mean that angular momentum is conserved or linear momentum is conserved. Now, linear momentum is conserved if you have internal forces only, and the internal forces, due to Newton's third law, they cancel each other. So the total net force is equal to 0. Then linear momentum will be conserved if you have only internal forces. If you apply an external force to your system, then linear momentum may not be conserved. So you actually have to run the calculations. But one thing you can look at from the expressions of the forces, if you see that the force depends on the spatial degrees of freedom only, or the potential, then when you calculate the curl of the force, if that is 0, then energy is conserved automatically. You don't need to think. So if the curl is equal to 0 and spatial degrees of freedom only, energy will be conserved. And that does not mean that linear momentum and angular momentum are conserved, as you will see from exercise 3. Any questions to these things? Okay, so one of the things I want to do now, before we dive into the 2 exercises I mentioned, and you should also feel free to ask about the other exercises in the homework, is to give you some hints and advice about both the numerical exercise and also some of the other exercises, if that is okay. So we spend more of the time today on looking at the exercises for this specific homework, which deals more with actually gaining insights about these conservation laws. So I just need to remind myself if there was something else I wanted to say here. Yeah, there are 2 small things I wanted to say. So when we said this, if you now look at this exercise, I mentioned this exercise 3 in this homework, and there you're given a potential which looks like x, y, z. and this has a constant a. So this is a constant. And then it's multiplied with the exponential, and then it has as argument x squared minus c squared. And this is divided with another constant. So these two guys, little a and big A, they are constants. Now, in this specific case, what you're going to find out when you calculate the curl, so let me just quickly remind you of that, because you will need this one when we are dealing with one of the exercises. This is going to be given by d of dy of fc minus d dc of f of y. And this is multiplied with a y component. And then we have the component in the y direction. So then we would have a d of dz of f of x minus d dx of f of z times j, the component along the y direction, plus a d dx of f of z minus, sorry, f of y. This is a y here, minus d dy of f of x multiplied with k. Now, in this specific case, if you now look at the derivative of the y component, can you immediately say, without doing any calculation, what the value should look like? 0, because there's no y dependence, right? So that's pretty obvious. So that means that all the terms which now involve derivative with respect to y here and y here, they will be 0, because there's no component in the y direction for the force. And what you're going to see in this specific case when you run the calculation is that the curl is going to be equal to 0. So this is a conservative force, but you will see that angular momentum and linear momentum are not conserved. So you cannot deduce that these properties are conserved immediately. So that's one of the things to think of. And when you see a specific problem and you have a specific force, then it's something which you have to check whether these quantities are conserved or not. Then there is another exercise which I wanted to say something about, and this is exercise 5 in the same homework. In that specific case, suppose now that we have a potential which is v of x. So this is not as part of the exercise, but suppose now the potential is given like that. That's normally called the harmonic oscillator potential, and we will be deriving that one when we start with harmonic oscillations. The derivation of that is a Taylor expansion around the minimum. And we are going to drop higher order terms when we perform a Taylor expansion. So that's a potential which you can actually derive from approximating oscillations around the bottom point. And the harmonic oscillator is something you're going to meet again and again when you study physics. When you come to quantum mechanics, this is one of these potentials where you can actually solve Schrödinger's equation analytically. And the harmonic oscillator has an infinitely many nice properties. And you're going to encounter this gradually. Now, if you now look at the usage of the gradient, we know that the force now, since this depends only on x, so F is now, if we look at the force, we use this expression of V of R, and now we have only the x component. Then we see that F goes over to f of x, and then we can skip the vectors. And this is simply minus d, there's only one dimension, of v of x. And then we see that this becomes a famous expression, which we have seen before, which is k times x. And k can be a material-specific constant. If you have one of these exciting systems, which you've probably seen from high school and on, where you have a block which is fastened to a spring, and then just oscillates back and forth. I don't know how many times I've seen that problem, and it's so boring. So when I began at university, we started with mechanics, and then we had a block which was sliding back and forth. I said, no, not again. But anyway, this is a useful quantity which you will see in many physics modeling. And you see now that you can actually derive the force which you have seen in many applications. And this is typically called a spring force. Now, the thing which is interesting here is actually that one of the things which allows us to gain a lot of intuition about the forces and the way the system is going to behave is to plot the potential. So plots of potential surfaces are extremely useful. So let me try to explain why these quantities are useful. Because you can actually look at the potential surface, and from that, you can infer how the system is going to behave. And that's extremely useful when you want to develop your insight about a physics problem. So if you look at the harmonic oscillator, and I hope you don't get offended if I ask questions about it. So if we now plot this harmonic oscillator potential as a function of x here, v of x, this is going to look something like this. Suppose now we place ourselves initially in this position x0. This is our initial position. And we assume that v0 is equal to 0. So that means that the total energy, since we have zero velocity, is simply 1/2 of k of x0 squared. So if you now, this is obviously a position which it cannot stay in, right? Because if you look at the potential, well, if you place a boulder or an object and you just leave it, it's just going to oscillate back and forth, right? So if I don't have any friction, if I now say that this object is going to move in this potential well, and I don't have any friction, it means that I would actually reach this new point here. And so we put 0 here, and we could say that this is minus x0. So the object is going to oscillate back and forth in here. And since there is no friction, it means that when it reaches the bottom, where we put x equal to 0, then the potential energy is 0, and then all the energy has turned into velocity. So that sounds reasonable, right? You've probably seen this many times. But in the exercise, you're going to get a potential which looks a little bit different. So in the exercise, you're going to find a potential which looks as follows. So we're going to have a v of x, which is going to be given by k of x squared divided by 2 minus this constant k times x to the power of 4 divided by 4 times the parameter alpha squared. And you are free to choose the parameters, and I always put parameters equal to 1 because that simplifies everything, and I put k equal to 1. And when you make a sketch of this potential, it's going to look something like this. And there's going to be an x0 here. There's going to be a minus x0 here. Now the question is, we are not going to have any type of friction. And I put myself in this specific position, which I'm going to call x1. And also here I put v0 equal to 0. Now, is this object going to be able to escape the potential? No. So it's just going to oscillate back and forth in the bottom of the potential. So if it's going to escape, we would need a potential or values where we actually are here. So that means that the velocity or the value of x which is needed in order for this object to escape the potential, it means that we would have an energy value which corresponds, if it has velocity 0, to the potential energy at that point x0. So from this object, or from this potential, you can actually say something about how the motion of this object is going to look like. So when you solve it either analytically or numerically, what you're going to see then, if you give that object an initial velocity v0 and position x0, then the object is going to escape. And then it will just leave the potential And what you will typically see then is that the velocity and the positions will just correspond to the case where the object is disappearing from the potential well. Now, if we want to be a little bit more realistic, we are going to have potentials when we come to the solar system. We are going to see potentials which are going to look like this. So let me just plot it. This is as the distance between two objects, and the potentials may look like this. So have you seen potentials like that before? So if I take the gravitational potential and plot that as a function of the relative distance between the Earth and the Sun, this is the way it's going to look like when I plot it in spherical coordinates or polar coordinates. So let me now ask you one thing, because this is something we are going to meet a little bit later, and I'm going to repeat these things. Suppose now I have this is the potential energy. Suppose I have a total energy which corresponds to this value here. This is my total energy of the system, let's say the Earth and the Sun. Can we say something about the type of orbits which the Earth is going to take around the Sun? So if you think of 0, r equal to 0, as the Sun being placed there, right? So now just think of this r as the distance between the Earth and the Sun, and the Sun would be located here. And it's a massive center, and it doesn't move. So if the energy now oscillates between these two, it has the same value because energy is conserved, but it oscillates between two values of r. One of these values, the shortest distance, has a name in astronomy. Has anyone encountered that name, the shortest distance between the Earth and the Sun? The perihelion. And then we have the longest distance, which is the aphelion. Perfect. So if you have this energy in this curve, this is going to correspond to an Earth which moves in a fixed orbit around the Sun, and it doesn't leave that orbit. If I, on the other hand, have an energy which corresponds to a value here, that is going to give us what we are going to call hyperbolic orbits. And then the Sun will still stay in its mass center, but the Earth will no longer have a steady orbit around the Sun. It will actually escape. So this is a typical example of just you watching at the graph, where you can just look at, okay, if it has this energy, this will happen. So if the energy is below 0 in this potential well, that means that it's going to be in a stable bound orbit. If it's above 0, then the system will be unstable. And then the Earth will escape the solar system. Something which we hopefully doesn't happen, at least in our lifetime. So we are coming back to these things, but making these graphs is extremely useful because that allows us to dig a little bit deeper and gain some insights about the physical systems without having done any calculations. And that's pretty neat. And you will see this again and again in all kinds of physics courses you're going to take. Now, the last thing I wanted to say something about is the numerical exercise. So this will be the exercise 6 in the same homework. And this exercise, we need now to set up a model for the normal force. So what we're going to have is something like this. So we have a ball which now hits the ground. And this ball has a radius, which we call for r. And it's under the influence of the gravitational force. There's going to be a normal force from the ground, N. And then we're also going to have a air resistance, which will act against it. So there will be a force F of D, the air resistance or drag force. And then we have the gravitational force here. Now, what we are going to do in this exercise is to use the spring constant force, and we are simply going to make a model for this normal force in terms of a constant, the spring constant. And we are going to have, since R is going to be in the y direction, so this is y, and this is going to be the x direction. So we are not going to put vectors, and this is going to be minus y of t, and it's multiplied with j, because it acts only in the y direction. And what we would have then is a force which looks like this. So we are going to assume now that when minus k of r minus this y of t, the position in the y direction, it's equal to that one when this y of t is smaller than r, smaller or equal, and then it's 0 when y of t is larger than r. So this is just a model which we're going to make. And what you need to do now in your code from homework number 3 is actually to add this specific form to the force, and that's it. So when I promised you that you're going to have a program to rule all exercises, this is actually what happens. You're going to just change the forces. So let me show you an example of what happens and see if we can then use this to develop some intuition. So if we now look at the, we go back to the screen here, to the slides, so the Jupyter Notebook. So let me do that, and before we switch over to exercise solutions. So if you now look at this problem here, what I did is to implement this force, and you have a good hint in this book by this Malte Sørensen. So I'm implementing the force here, and this is pointing upwards. And the only thing I need to do now, if this radius in the y direction is less than a given constant r, then we have a force, else we just have 0. And then I have my gravitational force, which comes in here. I have the air resistance with this drag force, and that's it. And with that, I can calculate the acceleration. And if I now set the initial velocities to 10 in the x direction and in the y direction, and an initial position in the y direction, this is now going to look something like this. And you can see now that when I could let this run for longer and longer times, and at the end here, you would just have a height which corresponds to the radius of the board. So that will be your final height here. So this is a more realistic simulations than the one we did in homework number 3. And now we're just adding a force. The problem with these forces, like the normal force and the air resistance, is that we don't have a fundamental force for them. And that means that we have to model them in one way or the other. So let me ask you one thing now. What happens if I put the velocity in the y direct in the x direction to 0, and I take away the normal force? No, sorry, the air resistance. So let me just show you. Before I make the calculations, I just wanted to trigger your intuition a little bit, because now you can play around. So suppose now I put the velocity, the initial velocity in the x direction to 0, and I take out this air resistance. So I simply have G and the normal force. And if you now look at the graph here, what would you expect? What should the graph look like? Yeah. Yeah, straight line up and down. And it just goes up and down. There is no air resistance. And it's just going to stay where x0 is equal to 0, right? So let's just check that and see that we have implemented things correctly. So let's run the code here. So this is one of these useful checks, which we can always do. Wow, this is exciting. Hey, can everybody see this fantastic line? So these are the kind of things which we can use now when we have a code like this. We can then trigger our own intuition. And this is a typical example of a problem which you could not have solved analytically. And now you can really explore your physics intuition. So, any questions so far? If not, I spoke for quite a lot of time here. I'm going to switch over to the exercises, these two exercises we put up, because I wanted to conclude this session with this kind of exercises which we put up here, and some of you may actually have done them. Not this one, but this one. So these are the exercises which I wanted to look at, and then we just stay with these till the end of the lecture. And if you wish to hang around a little bit more, feel free to do that. We have available the space till 5 o'clock. But now I'm going to stop the recording here.